there is a last homework, right? So we made a deal that there will be a couple more class exercises, but only one more homework to go, and that one more is now posted. And so I decided to reduce the number of problems, considering that probably you all are very stressed at this point. It's due on Monday, so please don't plan on asking for extension, because if there is a course doesn't have a final exam, we need to submit the grades soon after the semester ends.
Next Monday or the Monday after?
It's the Monday in the finals week.
Oh, okay.
It's already posted.
We're talking about like next Monday.
No, having said that, please don't leave that for that weekend and then start emailing me over the weekend. So what do I do here and there? You know that I like to help, but you know, over the weekend it's not always possible. So it's a little bit more work more work, even if it is 5 problems. Look at the problems. Look at them. And the numbers correspond to the problems in the textbook on Canvas. And I have spelled this out. No. In the textbook on Canvas. So there is on textbook, it's the same textbook, but an older version of this textbook is on Canvas. To make sure that everyone has access to that, I chose the problem numbers corresponding to that and not to this exactly. But it is written textbook on Canvas. Make sure you know what that is. If you don't know, please ask me. Don't solve a different problem. Yeah, a couple of people have done this before. So that's about the homework, and then there will be a couple of more class exercises, and then we are done with the semester. We only have 2 more weeks to go. Now with that, let's get back to continuing or finishing up the Flamen solution. And in the homework problem this time, you need to develop some solutions. So the procedures that we have gone through become important. It's not just plug in, and that's why I'm saying don't leave this for the weekend before, because that could be a very stressful weekend. So, and I'll be here, you can come and talk to me and so on to get that, to work on those problems. It's nothing hard or nothing that we have not discussed, but don't leave it for the last moment. And there is a plotting there that you have to use some plotting tools, whatever you are familiar with, so it takes a little bit more time, I would say. Okay, with that, I hope that you still remember from last week where we were. So we looked at Flamen solution. And that was when you have we define half a space, you remember that notion? And then you have concentrated forces y and x. And we like always, we picked some fragments of Mitchell's solution, and we kind of looked at the boundary conditions here. And remember the boundary conditions, the traction-free surface, and then we had an interesting kind of boundary condition, the equilibrium, calculated by integrating around these half circles. And we got to this solution. Before moving away from this problem, I just want to add a few things about this solution. So what is the nature of the solution? If you look at sigma RR and its dependence on R, what do you see?
Inverse.
It is proportional to the inverse of R, and this is somewhat something that we built in to this problem. Now, in terms of singularity of the solution, what is the implication of that? If you have R in the denominator.
As R gets very small, the stress gets really.
Right, so near the point of action of the loads at the center, you see, you have singularity. So there is really, you don't know what's happening there. And this is no surprise, because everything that we are doing in this class, we assume from the beginning force distributions. So this is kind of a problem which is not very good for elasticity theory, for field theory. It's just not a good problem. But let's look at this a little bit more closely. Now, you all agree that sigma, so I just continue this as a part of this previous lecture because it's kind of related. So I guess we all agree that sigma is has this dependence. So what happens to sigma RR? What do you think would be the dependence of ERR, the strain? The same. Now, what would be the dependence of UR, the displacement?
On both. What's our
We are just looking at R. Let's forget about theta for now. So what is the relationship in general? Exactly, the relationship between a strain and displacement. Remember, it's a derivative, so you have to. So it would be log R. And now that we are at it, if you look at a strain energy density, what would be that dependence? So the question is, what is a strain energy and density, right? So that's, what is a strain energy density? That's sigma times E, right? A stress times, it is 1 over R squared. So this is a little bit problematic. Look at UR, the dependence is log R. What happens when R becomes very large? Well, sigma R goes to 0, so does the strain, as we had built in the solution, and that's okay. But what happens to UR? Yeah, so that's kind of a problem, right? It's not nice. And for 0, we already discussed that we have singularity for a stress, and since we are in linear elastic regime, of course also for strain. So the solution has some limitations in the sense that, you know, we cannot do much about it. Now, the strain energy density, why do I bring this up? Strain energy density, if you integrate it, what do you get? If this is the problem that we are looking at, right, this looks like this. If I want to calculate the energy, what do? You integrate the strain energy density. You take an element, and then this is A, D, theta, and then you write like total energy is, you integrate some quantity which has dependence on R squared, and then you have R, dr, d theta, that would be the element, right? And you integrate, in this case, because it's a half a space between 0 and pi, and between, let's say, 0 and A. If you want to take all the energy which is inside that half circle. So what would be the nature of that?
nature?
What would be the kind of the
Scale.
yeah, not the scalar. What would be the dependence on the geometry here? It also becomes like kind of log A, because it's becomes like that. So this doesn't, if A is very large, this also becomes very large. It's just not really a nice solution. So there are some limitations with Flamen solution. It turns out that all these limitations are because of that point source. It turns out that if we replace that point source with a distribution, if we integrate the solution, all of this goes away. You smooth out all of that, and it becomes a lot nicer solution. So very quickly, we go through that, because that's kind of why Flamen solution is very interesting. Is not necessarily for this concentrated load, but when you integrate it to calculate the response in the half space to a distributed load. And so let's quickly look at that. We take into account, maybe I start a new page so it becomes nicer. Okay. So it turns out that the Flamen, I don't know why this happens. It turns out that the solution, a lot of these problems goes away if we try to solve it for this kind of loading. Now, we, for simplicity of the derivations, I just assume that x is 0, but this doesn't. It is still general. What we are deriving here. So x is the horizontal component of the concentrated force, and y is non-zero. And it turns out that in that case, it's easier. If you remember, x was to the left in that particular solution, and y is downwards. So it turns out that if we want to solve this, it's easier if we turn things back to Cartesian coordinates. We are not going to solve it again. We are just going to go from whatever formulation we had in polar coordinate to Cartesian coordinate. And if we do that without showing you how, trusting that you would be able to do that. So we had the equation for sigma or r, sigma theta theta and r theta. So if we turn that into Cartesian coordinates for this simpler case, we get this formulation. So this is for sigma xx, and then sigma yy, let me write here that this is Flamen solution in Cartesian coordinates. And then we have sigma xy but so far we haven't done anything. Basically, I've only looked at the solution that we had before, and I'm just saying that, okay, if we turn things around to Cartesian coordinate, this is what we are getting. But I want to get the solution to an arbitrary distribution of vertical load. And let me ask you again, do you remember what physical problem does this represent? Everyone except for Cody can answer. Contact in general. And it is a lot more interesting to look at a contact which is distributed. I mean, it's a lot more realistic most of the time. I mean, a point is it's too simplistic. So this is an important problem, and it's a useful one. So now, if I want to generate the solution, what is the trick we always do? What do we do? We are in linear elasticity. What do I have to do if I have the solution to one concentrated load? If I want to get the solution to distributed load, what is the trick? Integrate. Why can I integrate? Superposition, right? We can do superposition. So if I move this force, and the way it works, this is like a process that I'm sure you have seen in other places, and it's always good to kind of be easy around it. If I move this force to a distance I call C, the solution. Now I just write sigma xx, I don't want to repeat everything. How do we get the solution if we know the solution to the above problem? If I move it, how do I get the solution to this load? What do I have to do? Exactly, so I have to change the x to x minus c, right? So if I change the x to x minus c, and I keep y the same, I can very easily get the solution. I just write it for sigma xx, and the rest you can figure out on your own, right? Something like that. And once I have that, I can go and say, okay, I'm not interested in this. I want to get the solution to an arbitrary distribution of load. So what I would do is, I'm waiting for everyone to write. What I would do is, okay, now if I have a distributed load, this is, so x, y, I have this distributed load, can be anything, going from A to, what did I call this, B. Then I can take, this is a trick you have seen before, and it's very important. What happened? It's very important that that you be able to write it right on your own. So this one, you say okay. So if I take any position, I call this C, this is DC, and that would be F. So with this, I just take a very narrow part of this loading distribution. So my new Y now is what? Is FC times DC. Should not use this letter, it's hard to pronounce it. Right? So now going back to y that I had, I can just say, okay, now I can calculate sigma xx. The equation that I have before, instead of y, I just substitute f c d c, and then you just have x exactly what you had before. This is a typical process you do when you can integrate, and you integrate that for the range that you can have. In this case, happens to be a to b. And you can do this for others. The importance of this solution is that those limitations with the concentrated load disappear here, because you integrate, things become nice and smooth. So, and that's why Flamen solution is very powerful and useful, because you can use it for concentrated loads. Any questions? There are a lot of different, like, particular solutions in the book. If this is something related to your research or something, go back and look at those other ones. They become very hard to write or explain, but if you are interested, we can definitely talk about those other. But you should be able to now follow all of these solutions based on the things you have seen so far in this class. Now we go to the very last solution I want to discuss with you. So how many of you are using a Surface or a notebook or something like that? So this one, because it's already very complicated, I've printed out some, and it's already on Canvas. So if you want to take note on it, it's called Lecture 24 Williams Solution. If you look at under lectures on Canvas. No? You don't have access to Canvas? To invest as So I don't know how many, because I have only 12 copies. I assume that those of you who are using paper, let me press. I printed out things. Why doesn't mess with the system? Let me see how many.
I can try. I think you counted perfect.
You guys can,
Yeah, I think you counted perfect. I think you counted perfect. I think there's 12 without.
Really?
Yeah.
I just try to remember who has like a fancy. Oh, she already has the Surface. That's it. You can annotate. So if you are using a Surface, I know that you are using a Surface.
Where is it here?
It's there all the lecture notes are. Okay. So it's on the files lecture notes. So what I'm going to do is I'm going to update lecture. It turns out that actually it's perfect. That is provided if you guys. Actually, the printout is a little bit small. I apologize for that. So if you want to annotate over, make sure you can annotate. Those of you who are using a electronic version, and then we go through it. I have to give credit to Dr. Costanzo. It's a part of something I've borrowed something from him in that solution. So just to give him credit, we need to annotate. So I'm going to kind of explain things, and we just use that as the basic. Yeah, it would have been helpful if I actually showed you what I'm talking about. it's still a little bit tiny, right? Well, the first part is, so I'm not going to go through all the details. It's more to explain what's going on. Now, is everyone, the paper users and all the, actually, I mean, paper has a seal, I don't know, it's nice to write things, I think, by hand. So I have no bias or prejudice about any kind of usage, as long as you are following things and so on. Okay, so everyone is okay. Is there anyone who is still trying to log in into Canvas, push, all those things? John, you have that? Mika? Okay, I saw Lynn. Everyone. Okay, so the last solution, which is kind of important because again, one of the homework solutions is a version. It's something that will remind you of this lecture. Let's put it this way. So it's important, and I think the problems of cracks are definitely important in a lot of applications. And you see that the solution is pretty old, 1957. This is kind of the golden age of elasticity when people were developing all these solutions. And this is kind of the reference here for this talk. Before going to Williams' solution, so the name comes from this guy, Williams. It's not very different from Mitchell's solution, so don't worry about it. It's still similar. Let's just go very quickly, very quickly to what we did when we were developing Mitchell's solution. Zach, did you have a question? So if you remember, do you remember Mitchell's solution? We started with separation of variables. And we considered the form. Is everyone can see everything? Because I haven't done this in the class, make sure. We considered this form fr e to the power of b theta. And then, do you remember why we had to do a change of variable? It was the coefficients were not constant, so we weren't able to solve it, right? So we saw a pattern and we did this change of variables. I'm just trying to make you download that information you have. And then when we did this change, we could get a nice ODE, which could be solved using this characteristic equation. Everyone is somewhat remembering this. And then we looked at the solutions of this, and they are like that. But then we said, okay, for the solutions, we are going to Mitchell, focused on solutions which have this form, b equal to in, right? So n being an integer. So this built in some periodicity, because when you have, look back at the solution, when you have e to the power of in theta, using Euler's formula, you are going to get cosine n theta, sine n theta. So this builds in a periodicity in the solution. Now, when I motivated this whole solution, I told you when you have cracks, you can have multiplicity, because displacement can be discontinuous at the location of the crack. So this guy Williams, he said, well, if you want to use this for cracks, we don't have to have this in. B can be any complex valued number. So that relates Williams' solution to Mitchell's solution. So it's not a whole new solution, but it doesn't have that particular assumption in it. So you don't assume things to be in, B to be in, B can be any complex number. Does it make sense? Okay. So, Williams' solution. So if you do that, and for some reason here, that A in the Mitchell solution turns to lambda. And since Williams has used this, we are using this same notation. So don't be confused. So the solution has this form. And I'm not going to show you how or anything like that. So we are more going to examine this solution today rather than trying to look at the details. So what am I doing next? This is Mathematica. I don't know if you are familiar with it, but look at it. What equation is it? Biharmonic equation in polar coordinate. So here, if I put this solution, of course it's going to satisfy, but this is the proof, right, that it does. Gerald? Question? Very good. So this is biharmonic equation in polar coordinates. And what is important is that it satisfies the biharmonic equation for any value of lambda. So that's the solution. And it doesn't surprise us because Mitchell have already checked that, right? So we know that, but we are saying this. Now, what do we do always when we have a phi? What is the next thing we do? The stress potential is not that interesting. What we are interested in are stresses and then strains and displacement. So we look at the relationship between stresses, and it's much nicer, right? You don't have to write any of those big equations, so it's great. We look at how many of you use Mathematica. Okay, great. So, but the notation looks very like normal math, so it shouldn't be confusing. Is everyone okay by following even if you are not using Mathematica? Yeah, great. So sigma r, sigma theta, theta, sigma r, theta. You use the relationships in polar coordinates, you get that. Now we want to see what is going on with these solutions. Look at these solutions. What do we care about? What did we always care about? What do we want to look at these solutions? What do you think? Making sure you're not sleeping. What did we do before for Flamen solution when we had it? We looked at the dependence on R to see what's going on in terms of singularity. And if you do that, you need to look at these terms. Like the rest is some sign and some coefficients or something like that. The part which is multiplied are these. And R, now it doesn't show up in the denominator, but you have like negative 2 plus lambda. So basically what we have is R to the power of negative 2 plus lambda for all components of a stress. So what we want to see is, okay, what values of lambda is going to give us the kind of dependency that makes sense for this physical problem. And the physical problem is the problem of a crack. Maybe I should have explained this first. So we are looking at a crack. Now I'm exaggerating. Which has an opening to alpha, and I want to find out whether how to develop the solution locally around this crack, around the crack tip. Yeah. Okay. So, there is a picture coming up. Here it is. So we have alpha, and this is the coordinate. This is the problem that we are looking at. Now let's look at different options here. If lambda is between 0 and 1, so again I write this here, r to the power of minus 2 plus lambda, and lambda is between 1 and 0. So what are the limits? R to the minus 2, and then R to the minus 1. If we compare this to Flamen's solution, in terms of singularity, what can we say? In Flamen's solution, what was the singularity? What was the nature of singularity for sigma? Exactly. Let me have it here. So, and what happened here? When we had singularity, 1 over r, things didn't look very, very good in displacement. So, if it is r to the power of 2, 1 over r squared, it's even worse. So the singularity is stronger. If lambda is between 1 and 0, the singularity becomes even worse. So we kind of don't like that, because then we know that displacement is going to go towards infinity. It's just not a nice physical solution. So we don't like it. Let's look at lambda greater than 2. Again, I write here what happens then if lambda is now 2 or it's 3 or 4? Yeah, it's not dependent on r. Tom was shaking his head. It's good? Exactly. So in that case, the stresses are going to blow up at higher at distances. We don't like that also, because probably, most likely, we won't be able to satisfy the far-field boundary conditions. Everyone understands when I say far-field boundary conditions after the quiz last time? Far-field boundary conditions. Okay. We talk about that quiz at the end of the class, so if you are wondering. Okay, so do you agree that the sweetest spot for us is lambda between 1 and 2? It looks like if it is too large, stresses are going to be infinity. If it's too small, then displacement is not going to be nice, right? So the sweetest spot is lambda between 1 and 2. Did everyone follow this discussion? Okay. Now that we know this, we have to write boundary condition. What are the boundary conditions in this problem? Exactly. The crack faces are traction free. So if I, just like before, you use right? Don't be afraid if things look a little bit different, but it's still the same thing. You write the boundary conditions just like before. So you have the two n's. Can you tell me what n is for alpha, for theta equal to alpha? Exactly, it's negative e theta, because of the direction of the theta. And then when theta is, here is theta is what? 2 pi minus alpha, right? N is positive e theta. And then you can write, we have done this many times. You know how to write the boundary conditions. They're traction free. Boundary conditions. So TR is sigma r theta, E theta. I wrote here n theta, it's fine. N theta, which is 0. So, and T theta is sigma theta theta, n theta, that's also equal to 0. And this is for both theta equal to alpha and theta equal to. So this is in polar coordinates. This is how it looks like. And what you see here written, boundary conditions, is basically that. But nothing different from what you already know. And this n theta is 1 or -1, doesn't matter. Things are 0. And when you apply the boundary conditions, things become interesting. That's when the nature of the solution shows up. And as you can see, it becomes very, very messy, as shown here on the. So now you see why I printed this out, because. So what you want to find are these coefficients. If you do what you normally do to write this in terms of a matrix to solve, how do we ensure that we don't have non-trivial solutions? We want to solve this, so we have found that. Let me step back a little bit. So if it is not clear, these equations that you see here, this is one equation here, 2, 3. Look at the signs equal to 0. Each one of them is one equation. Now, what you want to find are these coefficients. What did I call them here? A1, A2, A3, A4. Right. So to be able to do that, typically what do? We have to solve a linearized problem. It's a system of linear equations. This is how we do it. So don't worry about the details here, but what you want to have is kind of set things up such that you have this kind of linear problem, and to get non-trivial solution, typically what do? Exactly, you have to set the determinant equal to 0. If it is too fast, you need to raise your hand and tell me. I'm enjoying that, how fast this is going. It's great. Because I don't have to write anything here. So the determinant has to be equal to 0 to get non-trivial solution. And all that complexity, when you do that, reduces to this nice little equation. So let us remember again here in this equation, what are we looking at? What are we looking for? I feel like we did so many things that maybe we forgot. So we started with a solution which had a variable lambda, which I said it's like A in Mitchell solution. And then we developed the stresses, applied boundary conditions. To get non-trivial solution, we got to this equation. So our unknown is still that lambda. That's what we are looking for. We kind of found the range where this lambda would make sense from the physical problem perspective, but what we want is to have this lambda, right? If we have this lambda, then we have our solution. So this lambda is the unknown. How about alpha? What is alpha? Exactly, this is alpha. Is this a known or an unknown? This is the problem we want to solve, so we know what it is. Just to make sure that when we are looking at this equation, we know what we are doing. So we want to solve this equation, which doesn't look very solvable, right, with analytical solutions. And we want to see what we get for lambda in terms of alpha. What is interesting is that, is there anything else here in this equation other than alpha and some numbers? It looks like lambda just depends on alpha. That's quite an interesting solution, right? So do we expect that from your understanding of fracture mechanics? Do you expect that the solution be dependent on the angle? Yes, you do, right? Now let's look at the limiting case. If this alpha was pi over 2, What kind of problem do we have? What did we call this half a space? Yeah. You don't have any sharp corner then, do we? No. If it becomes smaller than that, you always have some sort of a sharp corner. And you all have learned in fracture mechanics, the sharper it is it the better or worse in terms of the stresses? It becomes worse. Now let's see if this solution makes sense from what we knew before, right? Okay. With that, let's look at, oh, this looks ugly. Let's look at this solution. What I can show you, and hopefully everything is going to work. I will spend quite a little bit of time to make this work today. Yes, it's working. Yes, great. Okay, what we are looking at, I have to now tell you what these axes are. What we are looking at, maximize this. What we are looking here is we want to find the solutions for lambda. Okay, so every crossing in this curve, you know, solving that equation is not very trivial. So now imagine that every crossing of this curve with, this is a solution. So if, let's say here, the solutions would be lambda equal to 1.5, 1.6, 0.4, 0.5. That's what it means. And what I'm changing is alpha. So this is the solution of that equation. By changing alpha, we see how the solutions look like. If I'm increasing alpha from 0 to 3 times pi over 2. What is happening? Let me go from before. Okay, and also pay attention to the, we said that we like lambda to be between 1 and 2. This is what we like. This is what we want to have, right? Now, just pay attention to see what happens in terms of the lambdas. So, and again, every crossing is a lambda. And focus on between 1 and 2 because we don't like the other lambdas, which are smaller. Now, I'm increasing the alpha. Hopefully this is going to work here. We have solutions? Yes, we do. Do we still have solution? What do you think this alpha is? Exactly. So when you go above alpha equal to pi over 2, which is the half space, then we don't have a solution. And I can bring this all the way to the end, and no solution. And what was the solution at pi? When the alpha is very, very tiny, what is the solution? Between 1 and 2. 1.5. That's the worst case scenario, pretty much, right? When you increase it, what happens? It always just becomes larger. Does this make sense? It does. When it's very, very sharp, the solution is going to be worse. So the singularity, remember, the singularity is, now I have to go back. I cannot annotate this one. There were 2 lambdas? It's only one. This is only 1.5. No, both of them are solutions. But if it is bigger, things are better. So the worst solution is, so let me explain to that. Is this so far okay? This is what happened here. Now if we move back here, now this doesn't want to work. So this is what I showed you. So look here, we are looking at, so now, what happens, we know that the smallest that we got was for alpha equal to 0 and it was 1.5, right? So for alpha equal to 0, sorry that I write this very casually, but the write-up explains things better. Lambda is 1.5. When we increase the lambda, the solutions the lambda becomes bigger than 1.5. Is this a worse singularity or a better singularity? When lambda becomes a little bit larger. It's not as bad. Does it make sense? Yes, it does. So, this is a pretty cool solution. Do you all agree? Yes.
We're generally looking at the factor, but what is that? I mean, what range is there like a typical 210 really the crack out or something versus all the way? What is the accuracy?
You can plot it. So it depends really on alpha. So you see everything depends. Depending on your alpha, if you plot, then you see after how many it starts to go again. But I think it's pretty cool to see that, right? From what you guys all know what is going on here. And what is very cool is that for that particular lambda, for alpha equal to 0, so this corresponds to alpha equal to 0, as you can see here. If you substitute things as you expect, the dependencies on R, that was not my intention. I wanted to do this. Becomes 1 over a square root of R. Why I'm so excited about this? Because it does, but that's not why I'm so excited about it. Let's remember back what I told you about Flaman's solution, the bad one. So if we have sigmas, so here we have sigmas which are scaled with 1 over square root of R. What happens to a strain? What happens to a strain energy density? Exactly. And 1 over R, if you integrate it over a circle, then that singularity goes away. You can actually calculate that energy. So this is something that in fracture mechanics people calculate because you want to know how much energy is available to make a crack grow. If we didn't have that, if it was 1 over R squared, you would not be able to calculate this integral. So everything kind of falls into place, and this is the worst case scenario. This is now elasticity, right? We don't take into account the plasticity here, but it gives good estimation. There is, I don't know if you have heard of Paris law. It's still a very good estimation for how the crack grows. So we have elastic fracture mechanics, and there is, of course, the plasticity component that it will be added on, but it's not going to change things as much. We can always calculate this energy because the singularity just happens to be the perfect kind of singularity which we can deal with. So that's why complex methods are pretty good for cracks, because you do all these integrals that we just saying. Yeah, but if the crack is larger, everything is better. It's even easier. Remember? That's the worst case scenario. It's just, it cannot get worse. That's true. So that's a good point. That's a good point, but there are mathematicians and there are engineers, right? If your crack is very tiny compared to some length scale, which is important in your problem, for example, in your research, if the crack is very small compared to the wavelengths of the probing wave, then in mathematics you normally don't, you just consider it to be just a displacement discontinuity. So actually you are very interested in this situation. It's not zero. You know what mathematicians use it is?
So it's scale dependent.
Exactly. Yeah. If it becomes really finite, then it's not a crack anymore. It becomes like a sharp corner. It's more like a notch, exactly. Which is also a stress concentrator and all. So it's still that problem. So now there's one more cool thing about this. So now if you do substitute everything, you are going to get if you write everything in terms of this angle. I'm not sure exactly how to pronounce that letter. If you write everything, you are going to get a formulation like that. So I like to write only 3 lines here today and write these a little bit differently here. So it's the same equation, but actually just 2 lines. If you combine certain terms, you can write these 2 equations. The dependency is the same, so all we are doing is instead of using theta, you are using this other angle, which is typical in fracture mechanics. That's why. So if you write in terms of that angle, I'm just reorganizing the terms. There is a purpose to what I'm doing right now. And then sigma theta theta. Just playing with the trigonometric relationships. Let me check that I haven't done anything. Right. So if you look at these terms, do you agree that this part is symmetric with respect to this new angle? It's all cosine, right? And these 2 parts become anti-symmetric. It turns out that these symmetric parts, they are related to the opening of the crack in mode 1. If you are familiar with that, you know what I'm talking about. If not, mode 1 means this. And look, everything is symmetric. Makes sense that the stresses be also symmetric. Right? And then, of course, you have other modes. Mode 2 is a shearing motion, and this is anti-symmetric. I think this is pretty cool. So you can actually see the things you have learned before. If you don't know, just don't worry about it. That's really means this motion, and you can see that compared to the axis of the crack, this is anti-symmetric. Yes. Probably, it would be very complicated. So I don't know the analytical solution in 3 dimensions really. I don't know myself, but for sure. I mean, if you were able to solve that, probably people have done it before. Yeah, so it's I think pretty cool. Yeah, so I'm done early, but I want to go because this really helped Gerald. No, so okay. Let's no, we are not done. I am done, but we are not done, right? So and that's something good.